All right, here's number 22. So for the following exercises, consider an athlete running a 40-meter dash. The position of the athlete is given by d of t equals t cubed over 6 plus 4t, where d is the position in meters and t is the time elapsed measured in seconds. All right, so we have this function here that represents distance, right, over time, right? T is time, d is distance. Running a 40-meter dash, this is the distance traveled based on the time, right? The time that's elapsed, and that's t. All right, so what we're given is we want to find the average velocity. So remember, average velocity is that formula. Let's see, where do we put it? That formula, it's basically just the slope formula. Okay, if you want to just use the slope formula, that's totally fine with me. You don't have to remember all these different letters. It's basically just saying output 2 minus output 1 over input 2 minus input 1, right? And if you notice the way they write it, or the way that they give you your inputs is in interval notation, right? So they're saying, hey, on this interval from a to t, then find s of t minus s of a, those are the output values at those points, equals t over t minus a, all right? Not equals, but over t minus a. All right, so let's go back here. So basically what I want to do is I want to find the outputs at these what I want to do is I want to find the outputs at both of these points, right? Because these are inputs. These are x values or t values in this case, right? We're talking about time. So what I want to do is I want to find d for this first one for part A. I want to find d of 2.05 minus d of 1.95. Okay, so basically if I plug these in to here, then if I plug those in for t, then what I'm going to get is the output, right? So what we'll do is we'll find this, right? So I'm going to do d of 2.05. So what it's going to be is it's going to be t cubed, so it's going to be 2.05 cubed over 6 plus 4 times 2.05. Okay, so now we're going to do PEMDAS. So we're going to do exponents next. And you could just plug this whole thing in your calculator just like it looks. That's fine with me at this point, okay? And then don't forget to put the bottom here. So on the bottom, it's going to be just regular 2.05 minus 1.95, right? So it's just these b minus a or x minus a, or however you want to think of it. All right, so let's evaluate this. Go ahead and plug that in your calculator. All right, so based on my calculations, just this part here came out to be approximately negative 6.764 and change, okay? And so then we have to do the same thing with this one, right? So I'm going to plug d of 1.95 into my calculator, so that'll be 1.95 cubed over 6 plus 4 times 1.95, right? So I'm just putting 1.95 in for x. And that'll give me this, right? All right. And that gives us negative 0.3851, etc. Okay. All right, so then we subtract, so we have a negative, so that turns into a positive, right? So then we end up with negative 6.764 plus 0.3851 all over, and we have this on the bottom. You can calculate that if you want. I'll just bring it down and calculate now. So now I'm going to do the numerator. in the denominator. So it'll be, all right, so this is what we get. We get on top, ends up being negative 6.378875 approximately. Then on bottom, that's just 0.1. All right, so now we can plug this into our calculator, and what we'll get is negative 63.78, right? Does it say to round? Yeah, it doesn't say to round. Let's we'll do it by default. We'll just do hundreds, okay? So we'll go 63.788. So it's going to be 8. Then an 8 comes after it, so it'll turn into a 9, right? So that's our slope for part A, right? All right, so then we can do the same thing for this, same thing for this, same thing for this, and then for part 23, we're going to see if we can find a pattern, right? See if you can guess the instantaneous velocity of the runner at 2 seconds. So as we're getting closer and closer to 2, we should be able to see what the answer is there, right? What the slope is at that point, okay? All right, so find that trend. So that's basically how we do it. Let me just show you another major topic in calculus. Instead of finding the slope of a line at any given point, it's called the instantaneous rate of change. Instead of doing that, we can also find the area underneath the curve from one point to the next. This is called integration. This later on we'll see as an integral problem, but that's something we can do with calculus as well, which is pretty cool. So basically, you can have something like this. One way to approximate it is to actually use the rectangles here, okay? So you can actually find the height of each of these rectangles, and you can add them together, and that'll give you an approximate value for the area of the curve. Is it perfect? No, it's not, right? You can see some spaces here, right? So it's not exactly perfect, but it's pretty close, right? And the idea with the integral, or with integration, is the closer you get these rectangles together, the more it closes that gap, right? So that's where what we want to try to do is we want to try to get very, very thin rectangles, as thin as possible, if we want to get a more precise value, okay? All right, so here we have some rectangles. Those aren't very thin, and we have a lot of space in between here, so this isn't going to be exact. But if I want to estimate the area, really all I have to do is just find the area of this rectangle, this rectangle, this rectangle, right? So this rectangle is a 1 by 1, so the area would be 1. This rectangle is a 2 by 1, right? 2 high and 1 wide, so 2 times 1 is 2. So we're going to go 1 plus 2. And then this one here is a 1 on the second, or something by 1, but it's going to be 1, 2, 3, 4, 5 by 1, so it'll be 5. So 1 plus 2 plus 5 is 8, right? And so that would be the approximate area under the curve of this function from 0 to 3, okay? So from 0 to 3, that's the area of the curve under, or the area of the space underneath that curve. All right, so we don't have any of those in the lesson, but I just wanted to show you those. And here's another thing. This is multivariate calculus, where we can actually work in 3 dimensions and find volume instead of just area. We can find volume in 3 dimensions. All right, let me know if you have any questions. You can bring them to class. You can email me, set up some office hours if you like. But in class, we'll definitely have a time to work on this, discuss it, ask questions, and then work on our assignments. Let me know if you need anything.